In this video, I am going to talk about the use of the force model and frictional forces and how it fits into Newton's second law of motion. So I'm going to have here an object on a flat surface. It's going to be a rough surface, so there's some friction. Now people say rough and smooth, but physicists use a number called the coefficient of friction to describe how rough a surface is. So I'm going to say this coefficient of friction is 0.05, which is pretty small. Just for reference, asphalt on tires, rubber tires, is about 0.8. And this is a unitless number, okay, so I'm just putting unit of 1 here, that describes how rough this surface is. I'm going to pull with a force of 100 newtons, and the mass of this box is 100 newtons here, so 100, and I'm going to say the mass of the box is 100 kilograms. And we're going to find two things. We're going to find the frictional force that acts on it to oppose the motion, which is a script F. This is the actual force in newtons. We use the coefficient of friction, which is a measure of the roughness, to find the frictional force, as you'll see in a minute. And also we're going to find the acceleration rate of this box if we pull with this frictional force opposing our motion. So the first step of the force model is to draw a free body diagram. So we're going to draw an object right here. And we have mg, the gravitational force, pushing down, or pulling down from the earth. Fn, the ground pushing back up. The force I'm pulling with, capital F. And the frictional force, I'll draw at the bottom trailing edge, is a script F. So there's our free body diagram, all the forces acting on the object. Then I go to step 2, the sum of the forces. So in the since this motion side to side, I'm going to assume the positive direction is to the right and positive is up. So our normal axes. And here's my template. So remember, in the template, all I need to do is, if I have a good free body diagram, take the forces in the x and y direction and put them into the template. So I have a positive F because it points to the right, a negative frictional force because it opposes my motion, and I'm assuming this is going to accelerate, so I'll put x there, not 0. In the y direction, I have the normal force pushing up, which is the ground basically, and the gravitational force mg pushing down or pulling down, and then this will have 0 acceleration in the y direction because there's no up and down acceleration. In addition, when you do a force problem, you get a third equation for free. It's the frictional force equation, which says that the frictional force is equal to mu, the roughness, times the normal force. And for our case here, the normal force, if you just look at this equation right here, the normal force is going to be Fn minus mg equals 0. So the normal force is really mg. It's just a weight, which we saw in the lab. The weight would cause more compression between these two surfaces, and you have more interlocking, so more friction. So in effect, this becomes mu times m times g. Okay? So to solve, the first part, we're going to solve for the frictional force. So this frictional force is equal to mu m g, which is equal to 0.05 times 100 times 9.8, which is 4.9 newtons. Remember, this is a force, so the unit is a newton. The coefficient of friction is the number used to find the frictional force, and that's unitless over here. But the frictional force is 4.9 newtons. You can box your answer. Okay. Now, if this frictional force acts, what is the acceleration of the box? So if you look at the force equation in the x direction, I have capital F, the pulling force, minus this frictional force, which you just found, equals ma in the x direction. So a is equal to capital F minus script F over m, which if you put the numbers in, this is 100 minus 4.9 divided by 100, which gives you 0.95 meters per second squared. So that's the acceleration rate, assuming this frictional force acts. Which now you could take this acceleration rate and do a kinematics problem. But qualitatively, if you look at this, the larger this frictional force is, if that F is larger and larger and larger, then this acceleration rate's lower. So that makes sense. The more friction I have, the lower the acceleration rate. And if this frictional force were actually 100, you'd have 100 minus 100, and it would have zero acceleration, which would be a case where if you had something that's really heavy on the ground, like a big crate in the garage or something that's really on a rough surface, and you try to push or pull it, it wouldn't move. Because the frictional force is so great, it's large enough to oppose your pulling force. So there's an example of the force model with frictional forces, but it's the same procedure. Draw a free body diagram. You have the sum of the forces x, y direction, the frictional force equation, and then we solve as usual.